Hello from myself, Sarfnaz, and my colleague Adi. This tutorial is largely based on our experience as NLP researchers working in the health domain. We hardly get access to the data we really want, such as electronic health records, clinical notes, or GP notes. We therefore need to find other ways to contribute and hence find other types of data or even research avenues. This is the core of this tutorial. It is largely organized to summarize a couple of ACM surveys which we published in Epidemic Intelligence and Pharmacovigilance. We do not cover some of the very important but out of scope topics such as text pre-processing techniques or negation detection in biomedical NLP. Let's start with the title of the tutorial. We focus on application of NLP techniques for the healthcare domain. Let me clarify on the absence of healthcare dataset by defining what healthcare dataset is. What is a healthcare dataset? There are multiple definitions what health data is, which we listed three of them here on this page, but the running definitions that we will use in this tutorial is by EU GDPR 2016. Health data is defined as personal data related to the physical or mental health of a natural person, including the provision of healthcare services, which reveal information about his or her health status. So what is a healthcare dataset? Based on this definition that I just read, it is personal data related to provision of healthcare services, and it has to be sourced via a healthcare agency providing such services to individuals. But why are we assuming the absence of a healthcare dataset? We understand that some some healthcare datasets are public and available, such as mimic dataset, but given their limitations and that many of them are structured data, we are looking at finding complementary datasets and methods. Because there are problems out there for healthcare datasets regarding their accessibility, confidentiality and privacy, the fact that they may not be complete because not every patient visits a hospital, and the latency between different sources of a data, and most importantly, the maturity of healthcare systems in different countries are different, or even within the same country in different regions, it can be different. Some may be already digital and very advanced, and some may not be. So we also have to think whether or not any non-healthcare dataset um, is good for research. Um, but there are some evidence from studies that are published already showing such value that non-healthcare datasets can offer something. For example, White et al. In 2013 looked at the correlation between internet searches for drugs and adverse events, and they identified clear interactions, um, evidence of interaction between two drugs that caused, if taken together, they cause hyperglycemia. In 2016, Annie et al. In their paper Tweet Now See You in the ED Later observed a relationship between tweets that indicated alcohol use for a regional area in the US and the number of emergency department visits for alcohol abuse in a nearby urban hospital. In one of our own studies, we analyzed tweets leading to an asthma outbreak in Melbourne, Australia in 2016. In November 2000, on 21st of November 2016, Melbourne experienced the world's largest epidemic thunderstorm asthma, with thousands of people developing breathing difficulty in a very short period of time. Unfortunately, 10 people died that day. Should our early detection system, which only relied on tweets, been developed then, we should have been able to identify this outbreak 8 hours in advance before officials identified it. So our objective here is to show how NLP techniques can help healthcare even without using healthcare datasets. And we believe that there are advantages here, such as them potentially being more real-time, deployable, and applicable where digital healthcare systems are not sufficiently mature. So this is the roadmap of this tutorial, um, and it shows different modules that Adi and myself will cover shortly. Let's start with an introduction, which covers a short history of how digital health has been maturing over time and what challenges exist. Long ago, hospitals used only paper records. In November 2018, a news article talked about AI matching radiologists in screening X-rays for certain diseases. We have surely come a long way in terms of using AI for health-related applications. But where did all the power of AI for healthcare really come from? Journey of AI in healthcare probably started by Gello expression language. In parallel or even before digitization of records, there were some early AI systems, which we look at some of them here. They fall under the umbrella term of Clinical Decision Support System or CDSS. These systems link health observations with health knowledge to influence health choices by clinicians for improved healthcare, and they are there to assist clinicians at the point of care. So what did Gello language did? It was designed in 1984 as a programming language to query and build CDSS on top of health records. This was completely rule-based. Some of the early CDSS systems are criticized for their Greek oracle approach. The human expert was only at the data entry point, and they could not contribute any expertise of their own. Mycin was another popular expert system developed in the 70s by Stanford University. It meant to identify bacteria causing severe infections. It had an inference engine of approximately 600 manually created rules. It would ask a series of yes/no questions from the physicians to identify what the problem of the patient is. Mycin was never actually used in practice after all. This wasn't because uh, because of the weakness in its performance, but some observers raised the ethical and legal issues related to the use of computer in medicine back then. Similarly, Internist was another computer-assisted diagnostic tool developed by University of Pittsburgh. It used to ask a bunch of questions and to identify what problem the patient might have. The practitioner basically answers the questions that are posed by the system, and the main thing for this system was that it would not work if a patient had multiple conditions. Some other examples of similar systems developed before 1999 are listed here in this slide. These systems are mostly uh, described in this paper, which was published in 1999 with the title Natural Language Processing and its Future in Medicine. This paper, which was written in 1999, also states that NLP is likely to become more important shortly because of healthcare economics, and that web-based technology is becoming pervasive. There will be continuous work on voice recognition, and it's likely that we produce standard terminology and output forms due to initiatives such as UMLS. And again, let's think about it. This is written 20 years ago. And then in 2018, there's an article with the title, Will Doctors Be Replaced by Artificial Intelligence? Digitization of patient records is one important step towards digital health. Understanding the value of information technology for communication and dissemination of medical information was recognized in 1997, where there were efforts around computer-based patient records, or what they call the CPR. And there were two main reasons for that. One was evolving role of the primary care, since it's the first point of contact for the patients, and CPR could empower them. And second was integrated delivery system. Information system could combine healthcare providers, service providers, and other facilities. This paper, published in 1997, The Computer-Based Patient Record, an Essential Technology for Healthcare, lists hallmarks of computerization of patient records, as is listed here. So these are actually quite important because some of these are still hold true today. So, for example, number one, integrated view of patient data. This is something that information retrieval approaches for different forms of data can achieve. Access to knowledge resources. This is where standardized medical ontologies come into place. Or clinical decision support. Right now, there are several AI approaches on different kinds of data that make this happen. Back to this diagram, the transition from paper-based systems to digital systems, right up to AI-based systems to scan medical documents, has been a long journey. In this tutorial, we focus on the textual part of things, with of course a very special restriction of absence of a healthcare dataset.
Hi, my name is Aditya, and now I'll continue with the second module of our tutorial, Datasets. In this module, we'll be talking about the sources of these datasets, annotation strategies, and ethical principles. So the title of our tutorial is NLP for Healthcare in the Absence of a Healthcare Dataset. Like Sarnaz has discussed, a crucial component of the title is absence of a healthcare dataset. So in terms of non-healthcare datasets, we would like to discuss where these are obtained from, how they are labeled, and what ethical concerns may be relevant. Let's now discuss where these non-healthcare datasets can be obtained from. This paper from 2014 describes two types of sources for non-healthcare datasets: demand-based data sources and supply-based data sources. Demand-based sources refer to sources that reflect demand for information, which means the data in these sources is generated as a result of users expressing need for information. For example, this could be in the context of, say, search queries, where a user requests information about a certain topic. The advantages of demand-based data sources are that while they are useful in terms of providing aggregate information about large communities, as in the case of search queries. They may also be restricted in terms of access and in fact may have limited context, as we will see later. The second category of sources are supply-based data sources. These sources are essentially large-scale platforms which allow users to share information, in other words, supply information. The advantages of supply-based data sources are that they can provide large-scale individual information, but because the text tends to be longer than, say, search queries, which are a form of demand-based data sources, typical challenges of ambiguity in NLP also appear when NLP for healthcare is being applied to supply-based data sources. Let's now look at specific kinds of data that can be used for NLP for healthcare. The first kind is search queries. Anonymous search engine query data in the form of keywords that the users have searched for can provide an insight into their beliefs, behaviors, and interests. For example, the Google Flu Trends project was a project that used volumes of queries or terms related to influenza in order to predict the number of influenza infections that can be expected in a community. This was done in terms of top queries from different states in the US, which were used to predict the influenza counts. The advantage of the Google Flu Trends project was that it was large scale and the data was potentially anonymous because it used aggregate data. However, the disadvantage was that the access was limited. There are additional challenges of using search query data, which we will discuss later in the tutorial. The second data source is news articles. News articles may contain, say, health-related news, and therefore, in fact, before social media platforms became widely used, early work in epidemic intelligence involved the understanding of information in news articles. For example, this project from 2008 called Health Map was a monitor of news articles related to different diseases, and it was actually able to detect some of these outbreaks via news articles that were reported in smaller or less popular newspapers. Health Map exists even today. This paper by Lejeune et al. From 2010 uses news articles from multilingual sources so as to provide an understanding of a wider pandemic situation. The advantages of news articles are that because they are written by professional journalists, they tend to be formal and likely to be well written, as a result of which NLP tools such as, say, parsers could be applied more effectively. The disadvantages, however, are that news articles can be replicated across different sources because a news agency could supply their news articles to other news agencies which separately upload them, and therefore there may be duplicates in terms of news articles available on the web. And as is true for any news, health related news may also be subject to questions about its trustworthiness, and therefore trustworthiness of the source or the news needs to be ascertained. The next form of dataset is social media. People may report health conditions and health related issues on social media such as Twitter. Social media based epidemic intelligence, therefore, has been a popular area of research. The advantages of social media based epidemic intelligence or using social media for such tasks is that targeted health information can be available via public APIs. And in fact, there are technical obstacles that could exist for obtaining official records. In the absence of such healthcare data, social media data can be useful as a signal or an information. However, we understand that it may not be as reliable as official records for a variety of reasons. The next form of dataset that could be useful are discussion forum posts. There are several discussion forum posts on the internet related to the medical field that allow users to create discussions, ask questions, or share their experiences about topics. These topics may be general or specific, as in the case of Mumsnet, which is a discussion forum post where mothers discuss their experiences raising their children. Ask a Patient, which is a broader discussion forum post. The advantage of using discussion forum posts for NLP for healthcare are that because these topics can be specific, there is some sort of domain specificity in the kind of data sets that you would use. And therefore, this can actually be employed to understand specific issues related to the particular domain or related to the particular topic. For example, there has been some work which looks at discussion forum posts regarding cancer and provides opportunities to understand how awareness, impact, or emotional implications associated with the disease can be explored or handled. Because discussion forum posts allow possible anonymity, users also tend to possibly be more honest or candid about their feedback. However, discussion forum posts are not typically real time. They may often involve people describing experiences from the distant past, and as a result, there may be a decent amount of topic drift, etc. Because people may also talk about experiences of somebody else, this information may not be about the person themselves, but could in fact be about families supporting each other. During the COVID-19 outbreak, there has been significant research in using non-healthcare datasets for NLP for healthcare. So in the next two slides, we are going to summarize some of these datasets related to COVID. In terms of social media, there have been a few datasets that were downloaded using COVID-related terms. This first dataset by Chen et al. Is a large dataset of multi-million tweets, out of which 60% are in English, and these have been downloaded using keywords related to coronavirus. The second dataset is in multiple languages, where tweets in English and Japanese and posts from Weibo in Chinese have been collected for COVID-related terms. The third dataset by Hawari and others is a dataset of tweets in Arabic. There has also been some work which links multiple data sources. For example, this work by Zhu reports 2,000 news articles regarding coronavirus, along with around 140,000 tweets which shared these articles on Twitter. And therefore, the dataset allows an opportunity to understand how these news articles were shared on the social media, while also possibly exploring the veracity of these news articles. Other datasets that have been reported for COVID-19 are shown on the slide here. Wong and others report CORD-19, which is an open research dataset of COVID-related scientific publications. In fact, a pre-trained BERT model on CORD is also available in the link shown on the slide. Shahi and others present a dataset of around 5,000 COVID-related news articles that are labeled as fake news or not. Finally, Roberts and others describe TREC COVID-19 to facilitate IR systems related to COVID. They start with 30 initial topics, with 5 new topics being added in each subsequent round. So as we see, COVID-19 has spawned research in multiple fields of NLP where new datasets have been introduced. So while we've looked at what kind of sources of datasets exist, let us now look at how typically these datasets are labeled for the different NLP tasks. Annotation or labeling is the process of assigning supplementary information that can be used to learn specific tasks. It is important because let's look at this sentence. I have been coughing all morning, just took my cough syrup. If the goal is personal health mention classification, that is to detect if the sentence reports a health condition, it would have to be labeled as one among two labels, true or false. In this case, it would be labeled as true. If the task is drug mention extraction, then it would involve selecting subset of words in the sentence which correspond to the name of the drug, the medicinal drug, and therefore cough syrup get highlighted in the square brackets there. Another possible task is symptom normalization, where terms or words in the sentence get assigned with a predefined dictionary of known terms. Therefore, in this case, you observe that the word coughing gets associated with an ID which indicates the symptom of coughing, which is R05, an example symptom given in brackets. Typically, one comes across two kinds of annotation strategies in NLP for healthcare when using non-healthcare datasets. The first strategy is manual, where human annotators are given a list of guidelines and questions, and they completely annotate a dataset to create a labeled dataset. The second annotation strategy is hybrid, which consists of a combination of manual and automatic steps. Like I said, hybrid consists of a combination of manual and automatic steps. Let's first see what manual annotation is about. Manual annotation involves guidelines given to annotators in order to obtain the annotation. For example, this paper by Aramaki and others reports a dataset of tweets where each tweet is labeled as whether or not it reports a health condition, that is, whether or not it is a health mention. The annotator guidelines described in the paper state that a tweet should be labeled positive if two conditions hold true. The first condition is one or more people with flu exist around the tweet author. This makes it clear that the health mention may not correspond to the author themselves but could also be somebody around them. The second condition, which is clearly stated in the annotator guidelines, is that the tense is present or recent past. This eliminates tweets which could be describing an episode from the distant past because it may not be of relevance to epidemic intelligence when looking at tweets. Therefore, detailed annotation guidelines are helpful and important to obtain quality annotations from annotators. The guidelines in this case also specify that the tweet should be affirmative and not speculative. However, because manual annotation can be laborious and time-consuming, several approaches for hybrid annotation have been proposed. These approaches begin with a small subset of manually labeled annotation and expand to a larger subset. Let us look at one option which is given in this paper by Paul and Dredz. This is a two-step approach. They first download a set of 2 million tweets, and a subset of 5,000 tweets are manually labeled as health mentions or not. A classifier is then trained on these manually labeled tweets, and predictions are obtained on the remaining larger set of tweets. These predictions are then used as labels of tweets. The fact that they use predictions and not gold labels is also dependent on what they plan to use these labels for. Because the paper reports a topic model which only requires coarse labels and can allow some sort of error to be introduced in the labeling process, the authors do not require a high accuracy label for their dataset. And therefore, they say that it is acceptable to have a manually labeled subset and an automatically labeled majority set for the classification. The second kind of approach for hybrid annotation is given by Sadilek and others. They start with annotating a small dataset and in fact train two classifiers for the two-class classification task. The first classifier penalizes misclassification cost for one label. The second classifier penalizes misclassification cost for the other label. Because of these imbalanced misclassification costs, these classifiers tend to perform well for either of the two class labels. Then they obtain predictions on a larger set of unlabeled examples and then add high confidence instances to the labeled set. This is then used in an iterative manner to again train two classifiers with imbalanced misclassification cost. A similar approach for iterative annotation is given by Jiang and others. They also start with annotating a small dataset and train two classifiers. Then they obtain predictions on the larger set. However, in this case, they take these predictions and annotate all instances predicted as positive manually and select random subset of those predicted as negative for annotation. These manually labeled instances are then added to the labeled dataset. One sees that the proposed method in this case lays emphasis on getting the right annotations for the positive class as compared to the negative class. And therefore, all instances that are predicted as positive are verified to indeed be positive. When dealing with non-healthcare datasets, it is also important to be cognizant of what kind of ethical concerns may be relevant when using, creating, or annotating these datasets. Two concepts come to mind. These are confidentiality and privacy, which are important in medical documents. Confidentiality refers to the obligation of professionals and health workers to not disclose information. This is codified in the Hippocratic Oath administered to medical professionals. Privacy relates to protecting an individual's control over what personal information and decisions may or may not be shared with others. In fact, authorization is granting the permission to view confidential information, not necessarily share it. In fact, when using non-healthcare data, the concepts of confidentiality and privacy play out in terms of a variety of ways. One factor is social stigma. Social stigma may adversely affect non-anonymized non-healthcare data. When users of social media are not aware of the kind of implications of the posts that they are putting out there, it may lead to embarrassment or discrimination. For example, a Twitter user posting a personal health condition may not understand the possible implications. We tried this query, I pooped while sneezing, on Twitter and obtained 12 results. And therefore, non-healthcare data needs to be mindful of anonymization. For example, the Google Flu Trends project, which used search queries to predict influenza counts, had detailed specifications about anonymization of the data. Other work in ethics for non-healthcare datasets discusses protocols for social media research for health. This paper by Benton and others prescribes a set of steps that would be important to ensure that ethical concerns are respected and handled when dealing with datasets from social media for health. They prescribe constitution of review bodies. They discuss how informed consent can be understood in the context of social media. They also state that in the case of open source data, which is what a lot of social media content is called in the context of NLP for healthcare, there could be variations in what one is allowed or not allowed to do. They also discuss provisions such as statement of responsibility from the researchers for responsible research conduct, separation of data from annotations using identifiers, and keeping in place specific requirements of organizations. This brings us to the end of this module called Datasets. Let's now move on to the third module, Structured Knowledge Resources. In this module, we will be describing ICD codes, looking at ontologies that can be used if healthcare datasets are not available. We're also going to look at how ICD codes and ontologies have been used for a variety of tasks. Structured knowledge resources find their origin in standardization in healthcare. As health records began to be digitized, medical professionals and the field experienced the need of standardization. Because doctors used multiple terms and these terms could be arranged in systematic manners, it was possible to understand the hierarchy of diseases and the body parts they affect via structured resources. As a result, several repositories and ontologies have been created and used for healthcare applications of NLP. An important step towards standardization in healthcare comes in the form of the International Statistical Classification of Diseases and Related Health Problems, known as ICD. This is a list of medical terms by the World Health Organization. The current version of ICD is ICD-10. This was first introduced in 1893 and is used in 194 countries. The ICD training on the World Health Organization website has this quote which says, "To make people count, we first need to be able to count people." ICD-10, because of its standardization, makes this counting possible. It classifies diseases into several groups. 6 groups are communicable diseases, general diseases that affect the whole body, local diseases arranged by site, developmental diseases, injuries, and external causes. ICD codes are arranged in volumes such as the tabular list, which lists all conditions and provide character codes associated with each condition. For example, as shown in the figure here, malignant neoplasm of gum is assigned the code C03. The volume 2 describes detailed instructions to encode a particular condition. It also specifies the policies to record morbidity and mortality, which correspond to hospital statistics and death statistics. The ICD training says that when a patient arrives, the medical professional first looks up the symptom in volume 3 of the ICD codes, verifies that the code is correct in volume 1, and then verifies the classification and reporting rules as given in volume 2. Because ICD codes are used internationally and the original version is in English, they contain lists in British as well as American spellings. Standardization in healthcare has also derived from the notion of ontology. Ontology in philosophy means to study, to be able to study, and therefore ontology is the philosophical study of being. Ontology is a popular concept in artificial intelligence where it is defined as a formal specification of a shared conceptualization. Ontology is expected to have properties such as clarity, coherence, extensibility, etc. Ontologies have in fact been useful in NLP for a long time. This is an ontology that the field of NLP is familiar with. An ontology arranges knowledge of a field in the form of concepts and relationships between these concepts. In the graph here, concepts are indicated in ovals, while relationships are indicated by arrows between these ovals. Car is a concept central to this subset of ontology. This diagram here shows that a car may be instantiated either as an ambulance, limo, or a sedan, indicated by the hyponymy relation. A car is a kind of a vehicle or automobile, indicated by the hypernymy relation. A car has an airbag, indicated by the meronymy relation. This example here is a part of a popular knowledge resource for English, which has widely been used in NLP, called the WordNet. Several ontologies for medical applications have also been proposed. We discuss some of them in the forthcoming slides. One such ontology is the SNOMED ontology. SNOMED stands for Systematized Nomenclature of Medicine. This is a standardized multilingual vocabulary of clinical terms that are arranged in a hierarchy shown in the diagram. This consists of a domain, which is a specific domain to which an attribute can be applied. This is indicated by a concept of the type attribute. Each attribute is a relationship type used to categorize the semantic meaning of the source concept, and the concept is determined by the range, which is the allowable set of values that can be applied to each attribute. An example of such an hierarchy is shown in the figure here. MEDRA, or Medical Dictionary for Regulatory Activities, is another popular ontology that organizes concepts in terms of medical conditions and devices in a hierarchy that consists of a lowest level term, a preferred term, a high level term, a group term, and finally a system organ class. The MEDRA ontology also includes pharmaceuticals, vaccines, and drug device combination products. Biocaster is a popular ontology that captures syndromic knowledge in terms of concepts corresponding to diseases, symptoms, viruses, or syndrome, which is a collection of related symptoms that may occur as an indication of an illness. Biocaster ontology consists of relations such as has symptom that relates a disease with a symptom, or causes that relate a disease with the virus that causes the disease. The Biocaster ontology is available in 12 languages such as English, Japanese, French, Arabic, and Thai. Because ontologies were created at different points in time, there has been a requirement to link the concepts in these ontologies to each other. This effort by Stearns and others in 2001 combines two medical ontologies, SNOMED and clinical terms, manually by medical experts. Ontologies have also been linked automatically using comparisons of the terms in each of these ontologies. This paper from 2009 uses a Loom algorithm for automatic mapping of concepts into ontologies. The efforts around linking ontologies has also been captured in the Unified Medical Language System called the UMLS from 1989. The UMLS ontology, as shown in the figure on the right, combines medical ontologies of different kinds across different languages. It covers ontologies in 15 languages and has a meta-thesaurus that covers terms and codes from many vocabularies, as in the case of ICD-10, MESH, SNOMED, and others. The UMLS ontology arranges these terms in broad categories along semantic types and relationships between these categories along semantic relations. It also provides a specialist lexicon, which is a large syntactic lexicon of biomedical and general English, and tools for normalizing strings, generating variants of terms, and creating indexes in these medical ontologies. The UMLS Meta-thesaurus consists of concepts in the biomedical domain along with relationships between these concepts. Relationships could be of two types: associative relationships that, for example, associate symptoms with syndromes, or hierarchical relationships that consist of hierarchies of more general to more specialized illnesses. This is an example of the UMLS semantic network. As you can see, hierarchical relationships are captured in the form of types of organisms, such as fungus, virus, bacterium, etc. Injury and its physiological function are linked to each other using the relationship type disrupts. This ontology thus captures a subset of medical concepts, illnesses, and parts of the body system. If you want to look at different kinds of ontologies that have been reported for healthcare, NCBO BioPortal provides a library of ontologies. You can search terms in a browser where a term from different ontologies would appear on the screen. As a result, you would be able to see mappings between different ontologies. We saw ICD codes a while ago. Now let's see how they have been used for several NLP for healthcare tasks. This paper from 2017 performs automatic ICD code classification from text-based autopsy reports. In fact, descriptions associated with ICD codes can provide useful keywords to either create datasets or to assign labels to unsupervised clusters. In this paper from 2018, a dataset of tweets is applied to a topic model, and these clusters that are generated can be named based on the presence of these words in the ICD code descriptions. And therefore, ICD codes can be used for semi-supervised labeling of clusters arising from a topic model. ICD codes can also be used to create datasets, as shown in this figure here. In this paper from 2013, the authors first start with medical tweets that contain certain terms, partition them by time, identify frequent word sets in these word partitions, and look at the trends in these word sets over time. For trending keywords, Wikipedia is queried, and medical terms associated with these concepts in Wikipedia article are extracted and appended to the set of medical trends. This allows them to compare trends for formal as well as informal terms, as shown in the case of sore throat or a related term, runny nose. Now let us see how ontologies can be used for NLP for healthcare. In this paper, Collier and others provide an ontology-based approach to detect global health events. They monitor news feeds for multilingual health-related news, and based on the target keywords of symptoms of interest, relevant news articles that are then translated into English from the language that they were in. They use automatic machine translation, specifically Google Translate. Then, topic classification, named entity recognition, and event template recognition are applied in order to extract information from these news articles. These are finally mapped to concepts in the Biocaster ontology so that they can be represented and compared in clusters. Huang and others in 2016 used medical ontology to provide features for a classifier for illness detection. If a word in a tweet is predicted as an entity of interest, they map it to the concept present in the ontology based on similarity between the term and the concept. The concept themselves become features of a classifier that detects the illness. More recently, this work by Alsudias and others from 2020 uses English infectious diseases ontology, Arabic wordnet, and slang terms in order to create an infectious disease ontology for Arabic. The advantage of this method is that it incorporates non-standard terminology, uses slang terms, Arabic wordnet, and English ontologies in order to create an ontology in Arabic consisting of infectious disease terms. As seen in the diagram here, the last step of the ontology is in fact to seek help of a medical professional who provides an evaluation of the quality of the ontology. This brings us to the end of the third module. Let's now look at module 4, which is classification problems. In this module, we first look at typical problem definitions and then describe 5 types of approaches that have been reported for classification in NLP for healthcare. The first type of approaches are similarity-based approaches. Following that, we discuss topic model-based approaches, pipeline-based approaches, statistical approaches, and deep learning-based approaches for classification. Let's first look at typical problem definitions that have been explored in NLP for healthcare. The first problem definition is health mention classification. This task deals with prediction of whether or not a given text is a health mention. So I have had cough all week is a health mention, while ice creams can cause cough is not a health mention. Health mention classification is important to detect health outbreaks where individual health mention predictions correspond to events. The challenges in health mention classification are that while it may deal with identifying that somebody is reporting a health condition, targets may be important. A celebrity reporting a health symptom may be widely retweeted or discussed, but it does not correspond to a separate event. Adverse drug reaction detection is also a classification task that has been found to be useful for NLP for healthcare in the absence of a healthcare dataset. Adverse drug reaction, or ADR, is an injury caused by a medication. In this survey on ADR detection, we come across this table which classifies different kinds of data sources for ADR detection. Those pointed by arrows correspond to our tutorial here because they look at medical forum posts, social media, and search engine logs and try to detect ADRs in these datasets. It must also be noted that the survey paper identifies that these 3 kinds of data sources as low reliability. Sentiment detection is also important for NLP for healthcare in the context of, say, vaccine sentiment, which may deal with classification of sentiment expressed towards vaccine in a given text. The COVID-19 pandemic has also spawned a few new problem definitions and papers which explore these problem definitions. Because of a large volume of discussions on the internet about COVID, this paper by Wai and others presents a dataset of questions labeled with question categories such as prevention, symptoms, societal effects, etc. And they present results on a classifier which classifies question types for a particular dataset. There has been substantial work on fake news detection and misinformation detection during the COVID pandemic as well. Serrano and others present an approach to classify comments in a discussion forum posts as whether or not they indicate conspiracy comments. Cotonia and others in their paper report an approach for veracity detection of news headlines and the claims made in these news headlines. Let's now look at typical classification-based approaches for NLP for healthcare. This is a broad range of approaches that have been reported for the task. We will be discussing representative approaches in each of these types. Let's start with similarity-based approaches. In similarity-based approaches, notions of similarity between the label and the instance are used to model classes of interest. Semantic distance between words in the text to be classified and medical words of interest is a cornerstone of similarity-based approaches. Let's look at an example. In 2008, this paper matches n-grams in a news article with known dictionary of terms based on semantic distances. Therefore, they classify each news article for two output labels. The first output label indicates the primary location that the news article refers to, and the second output label is the name of the disease that the news article talks about. This other work from 2010 deals with multilingual news articles. They use similarity to extract properties from the news articles such as location, type, and type of illness, and as a result, they classify a news article as whether or not it is relevant to health if it was able to extract the type of illness. Topic models have been found to be useful to discover semantic concepts underlying large datasets, either labeled or unlabeled. And therefore, topic models have also been reported for NLP for healthcare. In this case, large unlabeled datasets can be used to extract structured topics of interest and as a result classify tweets. A common phenomenon is the use of asymmetric priors which are set on words corresponding to health domain so that these models can be bootstrapped. These asymmetric priors allow initialization of topics that will be eventually extracted from the topic model. One such topic model from 2012 is called the aspect topic ailment model. This is given in the diagram on the right. This topic model consists of three latent variables that are estimated by the model. L corresponds to a switching variable for general or health related words. X is the background words or the general words. Z is the specific type of element that this particular word corresponds to. This was applied later to Chinese microblogs by Wong and others. The goal of this topic model is essentially to learn phi, alpha, pi, and theta and use them to discover structures of words that correspond to different ailments and health-related words. The second kind of topic model is a temporal topic model, which uses sequences of symptoms as reported in the timeline of a user. The temporal topic model indicated in the figure on the right uses switch variables corresponding to X, which switches between symptom variables and general variables. Symptom variables are indicated by L and general variable are indicated by the letter Z. They also compute a tweet level symptom variable indicated by S. The diagram shows an arrow entering S and leaving S. This corresponds to a recurrence relationship between symptoms that have been posted by a user on their Twitter timeline. The next category of approaches are pipeline-based approaches. We call them as such because they correspond to a pipeline of NLP components where classification is combined with other additional information to be extracted. Typically, two systems come to mind when thinking of pipeline-based approaches: Global Health Monitor and Medisys. Global Health Monitor is a system that periodically scans news feeds, first performs topic classification in order to classify a tweet into one of the many predetermined topics. They then extract location information and the named entities in these news articles to be able to place them on the map. This map is shown in the visualization on the right. Medisys is also based on news articles which are first searched from feeds. A classification approach is used to categorize them as health related or not. Following that, an information extraction system based on patterns extracts information corresponding to location, name of the disease, information regarding the victim, and date and period. Statistical approaches use statistical classifiers which are dependent on features that are provided to these statistical classifiers. Some of these classifiers are shown in the table here. As you can see, in addition to word-based features such as unigrams, bigrams, or bag of words with feature windows, there have been qualitative features like emotion scores, user mentions, length of the post, pronominal mentions, etc. When thinking of statistical approaches, one remembers this important paper by Aramaki and others. They report an approach for health mention classification for tweets, where the goal is to predict a tweet such as, "My flu is worse than it was yesterday" as positive, "A bad influenza is going around in our lab" as positive, but in the normal flu season, 80% of deaths occur in people over 65 as negative. They annotate a dataset of 5,000 tweets for their experimentation. In this paper, they looked at context window-based features and apply support vector machine with a polynomial kernel in addition to other classifiers. The figure on the right shows what type of windows are helpful for health mention classification. As you see, the best performance is obtained when windows of left and right are used in order to predict the health mention in a particular tweet. However, it is the right window which results in the higher performance as compared to the left window. Deep learning based approaches for NLP for healthcare have also been reported in recent times. The state of the art uses two kinds of deep learning techniques. The first uses deep learning based embeddings as indicators for health mention classification. The second method uses deep learning architectures. Let's look at some of these methods on this slide. Lampos and others use embeddings to select unigram based features for flu detection. They experiment with embeddings learned on Wikipedia for a general understanding of the domain, and embeddings learned on tweets for a domain specific understanding. Dye and others use word embeddings to create clusters of concepts and use these clusters as features for a statistical classifier. Similarly, in our work from 2019, we compared GLOVE and Word2Vec, which are word-based representations, with contextual representations like ELMO and Universal Sentence Encoder. Similar approaches that use deep learning based embeddings have also been reported in this work called WESPAD, which stands for Word Embedding Space Partitioning and Distortion. They first learn a word embedding space from a large dataset. This is then partitioned on the basis of a dataset that has been labeled for the specific classification task. The sentence vector corresponding to a tweet is learned as a result of information gain based weighted version of individual word vectors present in the tweet. And this sentence vector forms the feature of a statistical classifier. Some approaches that have been used for classification tasks in NLP for healthcare using deep learning are also reminiscent of the development in the field. Wong and others from 2017 used recurrent neural networks to predict if a given tweet conveys influenza related information. They represent individual words in tweets by their embeddings learned from a large corpus. Then they apply bidirectional LSTM to obtain what they call a thought vector, which captures the meaning of the tweet. Then they apply a dense layer to obtain the prediction regarding the classification task. In our work from ACL 2019, we hypothesized that because symptom words may be used in a figurative sense, incorporation of figurative usage of symptom words in the form of features from a figurative usage detection module can be helpful. Therefore, as shown in the diagram on the right, features from a figurative usage detection module are appended to the semantic representation obtained from an embedding based representation. When the two are used together in order to perform health mention classification, we obtain an improvement of about 2% on the dataset by Karisani, which was described in the previous slides. This table is from our survey paper from ACM Computing Surveys. It summarizes the 6 kinds of approaches that we have discussed now by giving a general idea, the motivation, and typical challenges.
In this section, we're looking at information extraction, or IE, name entity recognition, normalization, and relation extraction, and we mostly focus on name entity recognition on user-generated text. Information extraction is the process of automatically extracting structured information from free text. It has applications in template filling and knowledge-based population. There are 3 major techniques that are involved in information extractions, including name entity recognition, or NER, relation extraction, and event extraction. In NER, types of entities of interest depends on application. In biomedical domain, some of these types are drugs, diseases, genes, proteins, adverse events. Look at the example here. I have been using probentin for 5 years now, and I really can't imagine my life without it. This is a review for this particular drug from Ask a Patient forum. If you are using this NER, for example, in application in pharmacovigilance, you probably are looking at extracting probentin as drug name and 5 years as the duration that a drug has been taken. In biomedical area, often types of entities that should be extracted can be complex. Some entities are discontinuous, that is, they span in different parts of a text. Some can overlap, or some of them can be nested. For example, here in this example, again from a review on askapatient.com, got severe lower back and leg pain, could not walk. Adverse events to be extracted from this particular piece of text would be severe lower back pain and severe leg pain. They overlap and they are discontinuous. There are a number of methods considered in the literature for NER. More older methods were rule-based, and some of them are dictionary-based. So they're looking up the piece of text to see if it exists in a particular dictionary. For example, if a drug name falls in, it can be found in a list of drugs, for example. More advanced methods has been classification based and sequence tagging based. For example, conditional random fields or CRF was state of the art for a very long time. More recently, some variation of BioLSTM CRF have been considered as a state of the art. So and have been using a number of different domains. Some of the methods use um, add extra lexical features to BioLSTM and CRF as well. I just mentioned here that biomedical entities are much more challenging than more traditional types of entities that have been looked at in the past. For a generic text, when they used to identify location, organization, and person types in a text, that is kind of considered as a more solved problem uh, for formal text, such as news, whereas there's still challenges in identifying biomedical entities in formal text and in informal text. As I mentioned before, some of the name entities can be complex. One of the types of complex entities is nested entities. That is, one entity resides inside another one. For example, the Israeli UN ambassador Danny, we have UN, which is an organization and sits within two-person entities. There are a number of methods out there proposed for identifying nested entities. One of them, proposed in 2018 by Wang and Liu, is a neural segmental hypergraph model that captures overlapping mentions. In mathematics, a hypergraph is a generalization of a graph in which an edge can join any number of vertices. They used Genia and ACE datasets to do their experiments. Another type of complex entity is discontinuous entity. That is when two or multiple parts of one entity are separated by some piece of text. One of the methods that is proposed for these types of entities is by Bang and Liu in 2019, and that's basically uh, ex, uh, expanding their previous hypergraph model to identify mentions which are discontinuous. And obviously, the justification here is that in the medical area, there can be um, these sorts of entities can be quite frequent. Um, Bang and Liu added an extra classifier to decide whether or not two identified text segments belong to one mention. One application of name entity recognition can be in pharmacovigilance. It can be done on formal text such as biomedical literature or informal text such as forums like Ask a Patient, Patients Like Me, or Daily Strength, and also on Twitter. Types of entities that we're looking at for an application such as pharmacovigilance would be drug name, disease, symptoms, or adverse events, which are slightly more difficult than the other three types of entities. Using social media for pharmacovigilance has been seriously considered. In an article, Recommendations for Use of Social Media in Pharmacovigilance, it mentions that many patients and clinicians have taken to social media to discuss their positive and negative experiences of medications, creating a source of publicly available information that has the potential to provide insights into medicinal product safety concerns. They recommend using social media in areas such as exposure during pregnancy and abuse or misuse of medicines. However, if we use social media for pharmacovigilance, we will always have one big barrier, and that's establishing causality. We can never establish if a certain drug has been taken as prescribed and the mentioned adverse events is related to that. So that is something that has to be identified through lab tests. There are a number of resources for working on NER in biomedical domain. Some of them are Genia, which is biomedical and it's on Medline abstract, so it's formal text. There's Craft, it's on full text biomedical journal articles. There's CADEC, it is on medication forum. Uh, SMM for health, it's Twitter data. NNE is named on nested entities and on news articles, and some of the biocreative corpora such as ChemNer track data. For those who want to just use an NER tool and not designing a new method, there are some tools freely available, in particular for uh, biomedical area. Some of these tools are listed here. For example, HUNER is based on LSTM-CRF, so it's pretty new in terms of technology as well. And there's other tools out there that are some of them are very dependent on what sort of entities that you might be interested. One area of information extraction that is particularly interesting in biomedical domain is name entity normalization. Once a name entity is identified, it can be normalized or assigned to a concept in an ontologies. This task is known as concept or normalization. For when you're working on a user-generated text or informal text in particular, it is necessary to translate those informal terms to formal. For example, somebody may mention Charlie horse as their adverse event of a drug, but what they actually mean in more formal text is muscle cramp. So that's the task of the concept normalization. Depending on the application, different ontologies are targeted. For example, when for adverse drug events, we might want to map the text or that Charlie horse to a term in an ontology called MEDRA. Again, for the application of pharmacovigilance, concept normalization has been looked mostly for drug reviews. One of the most popular tools in general is MetaMap. What it does is maps formal text to UMLS, and it works based on n-gram matching. It can make a lot of mistakes, and it is pretty slow. Uh, there are two more recent methods proposed. One of them was published in ACL in 2016, a CNN-based method with embeddings from Google News. Interestingly, this method outperformed RNNs and CNN with embeddings trained on biomedical central and retrieval-based methods. There was another method in 2018 in the Journal of Biomedical Informatics proposed that using RNNs with attention and similarity features from UMLS. Relation extraction is an important area of information extraction for biomedical area or applications in health. There are a large number of articles published every year and listed in Medline, and they may contain information on things like protein-protein or drug-drug interactions that are almost impossible to mine manually. And that's where relation extraction comes into play. Uh, there are a number of methods, NLP-based methods that are there that can mine some of those relations, and some of them actually use data mining techniques on top of NLP techniques. So next we're going to look at literature search and clinical trial search, which are retrieval problems. So we will cover a very brief introduction into information retrieval and biomedical literature search. Then we look at clinical trial search and a benchmarking platform. Search is often an initial step for biomedical text mining applications, and it's used to retrieve an initial set of documents that we will then process using NLP techniques. Oftentimes, we have information retrieval, then text classification, and then information extraction. For those of you who might not be familiar with the area of information retrieval, let's just recap what a search engine would consist of. Often there's an index of a document collection, for example, index of all the Medline abstracts. There's a querying facility that queries over the index. For example, you query treatments for lung cancer. That's an example of query. And you might have um, ways to process that query before sending it to the index. There will be a ranking function which decides in what order documents should be presented to the user. One of the most famous ranking function and one of the oldest one is Okapi BM25. And then we should decide how to represent the results to the user. For example, do you want to add in a snippet or do you want to highlight the key terms for the user? One of the major search engines in biomedical area is PubMed. It has the index of most of the biomedical literature published to date, and it largely offers Boolean search. Through track share task over years, some effort has been done to um, test different methods and systems for different types of search in general health area. One of them was clinical decision support track ran from 2014 to 2016, which would retrieve biomedical articles that were relevant for answering clinical questions about medical records. For example, what tests, what diagnoses, or what treatments are suitable for a particular patient. This is an example topic of a clinical decision support track. So as you see on the top, we have the note, uh, with all sorts of clinical text abbreviations and jargon. And there are two other sections to it, which is description and summary. They are created by experts on top of the note. Uh, and one of the things that NLP community could look at is how to summarize this clinical note to this summary, for example. Another potential area of search for health domain is searching over clinical trials. That is finding the right clinical trial for a patient. These trials can be accessed through websites such as clinicaltrials.gov. Trek ran a track between 2017 to 2020 that covered this task. Oncologists created synthetic cases, and each patient was presented with different information such as disease, the gene variant or mutation, and demographic. It changed in different years as well. Uh, for example, in 2018, topics included um, other medical conditions that the patient could have. This is an example topic from precision medicine track. So that represents a patient which has lung cancer with the gene related to that, demographic of the patient, and other the conditions that the patient had, for example, hypertension, um, and inclusion and exclusion criteria that existed in a clinical trial should match with all of these information that we have from the patient. So that's an example of a search. For the topic or the patient that we just saw with lung cancer, a good search engine that was designed within that track, precision medicine track, had to retrieve uh, both clinical trials and relevant literature. So for that patient, we have this on the left-hand side. We see the clinical trial that would match the patient, and on the right-hand side is an article that could provide some information useful for treatment of this patient. For those who might be interested in any of the health team tracks in Trek, such as clinical decision support, Trek genomics, or precision medicine, we have developed an online tool called A2A or Apple to Apples, which provides index over various Trek document collections. It provides different options of query for reformulation, query expansion, and ranking functions. Please feel free to check it out, and if there's any questions, happy to answer. In this module, we provide a brief overview of question answering and in particular patient question answering and share tasks that could help provide the means for developing question answering techniques. Most of us have searched for our systems looking for either a diagnosis or even a treatment. And that's where patient question answering systems come into place. Question answering is more specific than information retrieval because users are looking for specific answers to their questions. And when it comes to the medical area, a system should really be confident in the answers it provides, or it really should not provide any answers if it's going to be incorrect. It has been known that a third of people who do self-diagnose don't actually go and check that diagnosis with a professional and get help for it. And it's also important to know that patients often don't have the knowledge to know the correct terminology to search over credible sources such as medical journals. And even if they are presented with relevant resources, they might not be able to interpret them. And therefore, there are a number of areas that NLP research could help here. One of the major shared tasks that have been running since 2013, which helps NLP researchers working question answering in biomedical domain, is BioAsk. It provides some biomedical questions and their gold standard answers, um, which can be used for training or testing a system. Another shared task is MediQA. It's a shared task on textual inference, question entailment, and question answering. MedQA, Medical Question Answering Dataset, provides over 47,000 question answer pairs created from 12 NIH websites. The collection covers 37 question types, such as treatment, diagnosis, and side effects, which are associated with diseases, drugs, and other medical entities such as tests. Two sets of medical questions and the associated list of answers are retrieved by the medical question answering system, GQA, and re-ranked manually. This is an example question from MediQA shared task, which provides a question from a patient having his thinking about a particular condition and looking for information. So if you're interested in question answering for patients, this is one of the options that you could be looking.
We now look at the next module, time series monitoring problems. This is module 8. In this module, we will look at typical problem definitions of time series monitoring, which can be classified into two categories: problems that predict counts of infections versus problems that predict events of known outbreaks in the past. Why is time series important? Time series is important in the context of epidemic intelligence pipeline, as shown in the diagram here. Once health mention classification has been applied to social media posts, the timestamps of these posts can be used in the module called Health Event Detection in order to predict an outbreak over time or an outbreak over a geographical region. This depends on what information is available in the social media posts and what is the goal of interest for the project. Therefore, event detection uses time series data and monitors events of interest. For an example, this could be a disease outbreak or a surge in sentiment about vaccines, etc. A key requirement for time series monitoring problems is that the textual units must be ordered in some way. This could be using identifiers, this could be timeline of a user, or this could simply be timestamps attached to the textual units. Two broad areas of work in time series monitoring problems involves predicting counts of infections and detecting outbreaks. In terms of prediction of counts, a popular work is by Ginsberg and others, where they use search counts of the 45 million top queries across subset of states from the US. Weekly counts of top queries are normalized based on their occurrences, and a regression model is trained to predict influenza-like illness counts. Similarly, in 2016, Wu and others used support vector regression to predict influenza counts based on unigram counts in social media data. Sparks and others in 2017 predict tweet counts using Poisson regression model, and use features that capture seasonality and patterns of time series data in terms of hour, day of week, and day number. A key work is by Hayate and others who include factors that capture time lag for different words. They take into account the fact that a surge in the presence of a certain word may reflect in the influenza counts a few days after the word was seen. This is called as time lag. And therefore, they show time series graphs of counts of words in social media posts. For example, they observe that the word fever has a 16-day time lag in comparison with the number of flu patients, whereas the word injection has 55-day time lag with the number of flu patients. Therefore, they estimate this expected lag between tweet keyword counts and flu counts and incorporate that lag in flu count prediction based on tweet keyword counts. This notion has been useful in order to predict influenza infections ahead of time. This can be applied in general for prediction of infections of a given set of symptoms of interest. But a key question really is where does one get these counts from for experimentation? For Australia, the National Notifiable Diseases Surveillance System records counts of notifiable diseases and also segregates them in terms of additional demographic information such as state, year, age group, and sex. A detailed report for laboratory-confirmed influenza cases is also available. Other sources of data can be the Center for Disease Control and Prevention. In the context of COVID, several online monitors exist, one of the most popular ones being hosted by Johns Hopkins University. The second class of time series monitoring problems consists of situations where a known outbreak is expected to be identified as a part of experimentation. And therefore, this is typically retrospective in nature, where this outbreak is validated using public data. This work from 2008, as shown on the slide, uses news articles to detect health outbreaks based on the presence of health-related keywords in them. Similarly, this other work from 2016 show that the prevalence of influenza and Lyme can be detected 1 week ahead of time in comparison with reported CDC data if keywords in tweets are looked up. In addition to events, geographical region can also be the focus. In such a case, one would need to look at non-healthcare data pertinent to the specific region. Several APIs are available that allow us to focus or zone in on specific locations. For example, this work from 2016 focused on Ebola outbreak in London. Similarly, this work in 2018 centered around different states of the United States. We also showed how social media datasets can be used for early detection of epidemics. In this specific case, we looked at an acute disease event, which was a thunderstorm asthma outbreak in Melbourne. On 21st November 2016, a thunderstorm asthma outbreak occurred in Melbourne, Australia. In this work, which was published in a journal called Epidemiology, we aim to show if social media monitoring could have provided an early warning of this acute disease event, which transpired in a matter of few hours and caused significant threat to health of the community. We present a 4-step architecture which first performs initial selection. In this step, it selects tweets based on a certain set of keywords. Personal health mention classification, which uses a classifier based on NLP to predict if a given tweet containing a symptom word is a report of the symptom. We then finally use duplicate removal, where we retain the first tweet of the day by a given user. We found that this is useful because people tend to tweet often when they are reporting their symptom, especially because one of the motivators to report symptoms on social media is to obtain solidarity. And therefore, once a user receives this solidarity, they may want to engage with their audience. Finally, we use time between events based monitoring, that is TBE based monitoring, to detect an outbreak. TBE computes the time between consecutive tweets. If this time is shorter than expected, it means that tweets are far more frequent than expected. As a result, an outbreak is triggered. The graph on the left shows the outbreaks generated by the system for tweets containing the word breath and predicted as health mentions using SVM-perf, with the false discovery rate of 1 in 1000. The x-axis is the dates, while the y-axis is the number of alerts generated by the system. Points above the red line are the alerts generated by the system. We observed that the earliest alert on 21st November 2016 was at 8:55 a.m., which is around 9 hours before the official report, which records that the outbreak was detected on 21st November 2016 at 6 p.m. We also observed that for a variety of symptom words, as indicated in the table on the right, which is breath, cough, and other symptom words, and for different classifiers, we do obtain early alerts on the basis of social media. Similarly, COVID-related event detection modules have been reported. Cornelius and others present a Twitter monitor that performs many tasks for tweets related to COVID, such as personal health mention classification, drug name detection, sentiment analysis, topic modeling, and so on. Wang and others in 2020 also presented a retrospective study for COVID-19. Using WeChat, an index on a popular chat platform that returns the number of posts mentioning a keyword, they show that alerts were obtained 2 weeks before the outbreak announcement. We've now come to the last module in our tutorial, the conclusion section. In this module, we are going to look at a summary of what we discussed in the tutorial so far, and then we discuss some possible future directions. Let's go over the 9 modules that we've presented in the tutorial. In the first module, Introduction, we looked at the history of healthcare in NLP and identified that the journey of NLP in healthcare has been from paper-based text records to the state of the art today. In the second module, we focused on the absence of a healthcare dataset component of our tutorial, where we looked at possible sources of datasets and typical annotation strategies. We then identified that structured resources have been crucial for NLP in healthcare and have also been applied for healthcare settings where a dataset from the domain may not be available. Finally, we looked at different kinds of classification problems in the context of different problem definitions and approaches based on, say, topic models, statistical approaches, and deep learning based approaches. In the second half of the tutorial, we looked at information extraction problems in the context of biomedical NER and complex models which incorporate nested entities and extract them from text. We then looked at retrieval problems where we identified the relationship between search, information retrieval, and information extraction. We also looked at certain benchmarking platforms that have been used for NLP for healthcare. We then discussed question answering in the context of patient question answering, a useful application, and looked at shared tasks related to question answering in the biomedical domain. Finally, in the last module, we looked at time series monitoring problems that have been used to either identify trends in non healthcare datasets or be able to retrospectively detect events of interest. Based on the current work, certain future directions that are possible are in the context of adaptation to different locations and languages. In the context of the COVID-19 pandemic, we see it happening for a variety of settings. Because this is also focused currently on a specific set of illnesses, it may be useful to adapt it to different illnesses. Finally, reliability of information is crucial because of the non-healthcare dataset setting. And in the wake of the pandemic, there could be several misinformation going around. False alerts due to ambiguity in the text and accounting for changes in social networks and the behavior therein are also important future directions when using NLP for healthcare without healthcare datasets. We also believe that certain health events in social media are underrepresented and could be useful in the future. One such example that comes to mind are zoonotic diseases or diseases that are contracted from animals. So, in terms of final remarks, we would just like to say that as a community, we can produce healthcare records and non healthcare data. The non healthcare data can be in the form of text, which allows peculiar advantages, as we saw in this tutorial. We also discussed several possibilities of applications for this non healthcare data based on text. However, we acknowledge that what we discussed in this tutorial is a piece in the larger puzzle of AI for healthcare, because non-healthcare data could be in the form of information apart from text, as in the case of image or other data. Similarly, it is important that healthcare records be also used with artificial intelligence for useful applications. These healthcare records can be in the form of image or other text. The dotted line in this figure really indicates the scope of this tutorial, and we hope that we have been able to give you an overview and a flavor of how different NLP problems have been formalized for healthcare applications, even when official records or official healthcare data may not be available. We highlight that the wide range of these data sources and applications really point to making an impact in health using artificial intelligence. Thank you for your time. This was a tutorial by Sarnaz and Aditya.